All right, let's dive right into this. Welcome to today's explainer, where we're embarking on a seriously fascinating journey into the world of coordinate geometry. Now, if you've ever looked at a math graph and just seen, a random scattering of chaotic lines and numbers, trust me, you are absolutely not alone. But today, we're going to completely transform that view. We're demystifying the straight line. I want you to think of coordinate geometry not just as some dry math topic, but as a really intuitive visual map and a super powerful toolkit. And honestly, the best part is that we're going to build this entire world, starting with literally just 2 simple points. So here's the quick roadmap for our geometric toolkit today. We'll start with the distance between points, then move on to finding the midpoint, calculating the gradient, comparing parallel versus perpendicular lines, and finally, we'll wrap up with the straight line equation. Let's get to it. Section 1. Distance between points. The journey begins. Okay, to start building our map, we obviously need a reference. So what secrets do the coordinates 1, 3, and 5, 6 hold? I really want you to picture these 2 points sitting on a grid in your mind. Point A is sitting at 1 on the x-axis and up at 3 on the y-axis. Point B, well, that one's moved over to 5 and up to 6. They aren't just random, arbitrary numbers. They represent a very specific spatial relationship. There is a real physical distance between them. But the big question is, how do we figure out exactly what that distance is without, cheating and grabbing a ruler? Well, the source material gives us this brilliant 3-step physical process to calculate it, relying purely on the coordinates themselves. First, we find the horizontal distance. Just subtract the x-coordinates. 5 minus 1 is 4. Then we square it, which gives us 16. Second, we find the vertical distance. Subtract the y-coordinates. 6 minus 3 is 3. Square that, and we get 9. Finally, we just add those 2 squared results together. So 16 plus 9 equals 25, and we find the square root. And the square root of 25 is, beautifully, exactly 5. So the main takeaway here is that the exact straight line distance between our 2 coordinates works out perfectly to 5 units. Look at that. No ruler required. Moving right along to section 2, finding the midpoint, locating the exact center. Okay, so we know exactly how far apart our 2 points are now. But what if we want to meet exactly in the middle? To find this middle ground, without even needing to sketch the points on a graph, we just have to find the average. It's actually incredibly straightforward. Step 1, find the mean of the x-coordinates. We take our 1 and our 5, add them up to get 6, and cut that in half, dividing by 2. That gives us 3. Step 2, we do the exact same thing for the y-coordinates. 3 plus 6 is 9. Divide that by 2, and you get 4.5. And there you have it. That brilliantly illustrates how we arrive at our midpoint, the coordinate 3, 4.5. We've basically just perfectly balanced the scales between our start and end points. Which brings us to section 3, calculating the gradient, measuring the steepness. Now that we've mastered measuring the length and finding the exact middle of our journey, it's time for things to get really dynamic. Enter the gradient. This structurally connects our points by defining their slope, or in everyday terms, their steepness. Our source material defines this as the vertical distance between 2 points divided by the horizontal distance. Let's actually test this out with a slightly different second point just to make the math super clean. Let's use 1, 3 and 5, 7. Our vertical shift, that's the change in y, is 7 minus 3, which is 4. Our horizontal shift, the change in x, is 5 minus 1, which is also 4. Divide the vertical by the horizontal, 4 divided by 4, and we get a gradient of exactly 1. It's a perfect, steady incline. And hey, speaking of inclines, it is absolutely vital to visually understand what that calculated number actually means in the real world. A positive gradient, like the one we literally just calculated, means the line slopes upwards from left to right. Think of it like you're climbing a hill. On the flip side, a negative gradient means the line slopes downwards from left to right. You're sliding down the hill. You can and definitely should always use this quick visual check to verify if your mathematical calculation makes logical sense. Because, if you calculate a negative number but your line is pointing straight up to the sky, yeah, for sure you need to go back and check your math. Before we move on, there are 2 really special cases you absolutely must keep in your back pocket. First, if a line is perfectly horizontal, flat as a pancake, there is 0 change in the vertical y-coordinates. And since 0 divided by anything is still just 0, the gradient is 0. Simple, right? However, if a line is perfectly vertical, there is 0 change in the horizontal x-coordinates. If you plug that in, you end up trying to divide by 0, which, as we all know in mathematics, is a huge no-no. It breaks the system, so we call that an undefined or infinite gradient. All right, section 4.
Parallel versus perpendicular, how lines interact.
So now that we totally understand the gradient of a single line, we get to explore how multiple lines interact with each other. And the relationship between straight lines is dictated entirely by, you guessed it, their gradients. Parallel lines are just like train tracks. They will literally never intersect. Why? Because their gradients are absolutely identical. If line 1 has a gradient of 3, line 2 must have a gradient of 3. Perpendicular lines are a whole different beast. They intersect at perfectly crisp right angles, exactly 90 degrees. For this magic to happen, the product of their gradients has to equal -1, meaning if you multiply gradient 1 by gradient 2, the answer is exactly -1. One gradient is always the negative reciprocal of the other. It's a really neat trick.
And finally, section 5, the straight line equation, the ultimate geometric tool.
Okay, drum roll please. It is time to reveal the final master key that mathematically defines every single point that could ever possibly exist on a specific line. Let's look at this raw data table we extracted straight from the source material. On the left, we've got our x-coordinates, 1, 2, 3, 4. And on the right, their corresponding y-coordinates, 2, 4, 6, 8. So what is the common rule connecting every x and y coordinate in this table? Take just a second to look at the pattern. For every x, what exactly is happening to create the y? 1 becomes 2, 2 becomes 4, 3 becomes 6. I'm sure you see it. The pattern is crystal clear. Every single y coordinate is exactly twice the value of its corresponding x coordinate.
And that totally natural discovery leads us straight to the master formula of coordinate geometry, y equals mx plus c. This algebraic equation represents literally any straight line. The m stands for our gradient, our steepness, which we already talked about, and the c represents the y-intercept. That's the exact spot where the line crosses the vertical y-axis. Now, for the table we just looked at, the line would cross the y-axis at exactly 0, so our c is 0. And because the y value is always twice the x value, our steepness, our m, is 2. So the entire rule for that line is simply written as y equals 2x.
What makes this master formula so incredibly powerful is how easily we can just extract data right out of it. Like, if someone hands you the equation y equals 3x minus 2, you don't even have to bother drawing a graph. You instantly know the gradient is 3, so it's a fairly steep slope pointing upward, and you know it crosses the y-axis down at -2. If you see y equals -2x plus 6, boom, you know right away the gradient is -2, it's sloping downward, and it intersects the y-axis way up at +6. You can basically visualize the whole entire line just by reading the formula like a book.
But, and this is a really important quick warning from the source text, sometimes these equations like to wear a disguise. You can't just carelessly pull the numbers out if the equation isn't perfectly set up in that y equals mx plus c format. Take a look at 2y equals 4x plus 2. You might be really tempted to say, oh, the gradient is 4? Actually, scratch that. We need just a single, lonely y on the left side, not 2y. To fix this, we have to divide the entire equation by 2. This rearranges it to y equals 2x plus 1. Ah, now the real truth is revealed. The actual gradient is 2, and the intercept is 1. So remember, always, always rearrange first. Just before we finish up today, let's bring back this absolute magic number. -1. Remember, this is the ultimate foolproof test for perpendicular lines. If you multiply the gradients of two lines and get exactly -1, they cross at a perfect 90-degree angle. It's this beautiful foundational rule that ties together our entire geometric toolkit, from calculating the initial slope all the way to understanding how different straight lines interact within the exact same space. Well, we've covered a ton of ground today, starting from just finding the distance between two simple little dots, all the way to extracting massive structural blueprints from algebraic equations. But as we wrap up, I want to leave you with this final provocative thought. How can mastering these seemingly simple linear rules actually help us predict real-world data trends and handle physical tracking? Think about it, because ultimately, coordinate geometry isn't just about doing math on a piece of paper. It is literally the exact language we use to map our GPS satellites, to model complex financial trajectories, and to construct the entire physical world around us. So keep exploring, keep mapping your world, and I'll see you in the next explainer.